In this mini lecture, we'll learn about a third set of reactions of alkenes and alkynes. One of the first reactions that we'll learn about is how water can add across a carbon-carbon double bond. In the previous mini lecture, we learned how mineral acids, HCl, HBr, and HI, could add across the carbon-carbon double bond. And we learned that this reaction occurred via a carbocation intermediate. In this mini lecture, we'll learn how the elements of water, H and OH, can also add across a carbon-carbon double bond to yield a mixture of syn and anti-alcohols. The reaction conditions are quite simple for this reaction. They involve water in acid. Water in acid. In other words, dilute acid. Another way to write this is simply to say H3O+, which is the hydronium ion, present when we have water and acid being present, or writing dilute sulfuric acid. All of those indicate that we've got water present and we have acid present. One of the biggest problems with this reaction is that since it has a carbocation intermediate, carbocation rearrangements can occur. And so we're going to learn very quickly about a second reaction with very little practical value, the oxymercuration reaction, which can carry out the same kind of a chemical reaction but doesn't have the potential for carbocation rearrangements. So if we look at an alkene, as we did in the previous unit, we've now recognized that an alkene can act as a nucleophile. Acid, H+, or in the form of H3O+, is a good electrophile. And so this mechanism involves the nucleophile reacting with, the nucleophile being the alkene, reacting with the H3O+. So in our very first step of our mechanism, the carbon-carbon double bond attacks the proton of H3O+, and we break the hydrogen-oxygen bond. This gives us a carbocation intermediate. And as we saw in the previous mini lecture, we form the carbocation intermediate that is the most substituted. In this case, a secondary carbocation instead of a primary carbocation. And this is the origin of Markovnikov's rule in the addition of HX, and here in the Markovnikov addition of water. The hydrogen, being the electrophile, goes to the less substituted carbon. Once we form the carbocation, it is an excellent electrophile, and it will react with a wide variety of nucleophiles. In the previous mini lecture, the nucleophile was X-, chloride, bromide, or iodide. In this reaction, a water molecule can act as the nucleophile. And one of the lone pairs on the oxygen attacks the carbocation center, the carbon of the carbocation, leading to a new species that now looks very much like an alcohol, but it has an extra hydrogen on it. So we refer to this as a protonated alcohol, or alternatively the conjugate acid of an alcohol. Last semester we learned that protonation of an OH group can cause the OH group to become a good leaving group from what was previously a poor leaving group. Here we're simply doing the opposite kind of a reaction. Instead of causing the OH group to fall off, we are putting an OH group onto our alcohol, onto an alcohol product. So this protonated alcohol forms, and then a base, which can be another water molecule, comes in and pulls off the proton, and the electrons go back to the oxygen. And so overall, now we regenerate a molecule of H3O+, just like what we had to begin with, and net we've added a molecule of water, H and OH, across the carbon-carbon double bond. Since we have a carbocation intermediate, which is planar, our water nucleophile can add on the top or the bottom. In other words, the hydrogen and the OH group could add on the same face of the alkene or on opposite faces. So if we wanted to write this mechanism in words, our first step would be an alkene, which is our nucleophile, attacks H3O+, which is our electrophile, to form a carbocation. In the second step, our carbocation reacts with a water molecule, which is the nucleophile, to form a protonated alcohol, or in other words, a conjugate acid of our alcohol. And then in the final step, a water molecule acts as a base to pull off a proton and to generate our product, which is the alcohol. Let's look at this reaction in the context of an example. We have an alkene present in our starting material. This alkene has unequally substituted carbons. The bottom carbon has one carbon on it and one hydrogen on it. The top carbon of the alkene has two carbons on it, and as a result the top carbon is more substituted, the bottom carbon is less. In this reaction we're adding water, H2O, in a Markovnikov addition. So as a result, the H of water, which is our electrophile, is going to end up on the less, and the OH of water is going to end up on the more substituted carbon. Now in this particular situation, we form a CH2 group here on one end. And so we can't tell the difference between syn and anti-addition. Overall in this reaction, we generate an achiral product, and there are no mixture of enantiomers or cis-trans products formed in this reaction. Now, a related reaction is called the hydroboration reaction. It too allows us to make an alcohol from an alkene, but the mechanism of the reaction is vastly different. And in this particular reaction, we will not have to worry about electron pushing because it's not a polar reaction. It's what we heard in the beginning of Chem 311 is called a paracyclic reaction. Bonds are simply being made and broken in the transition state. And so as a result, we fortunately do not have to do electron pushing and drawing the mechanism. So the reaction is identical in the case of hydroboration. An alkene is converted into an alcohol. One end of the carbon-carbon double bond receives a hydrogen. The other end gets the OH group. The difference with this particular reaction is that it's non-Markovnikov. Now that means that the hydrogen of the water molecule that gets added is added to the more substituted carbon, and the OH gets added to the less. And so this complements nicely the addition of water that we learned about on a previous slide. We'll have to look at why this particular switch in reactivity or orientation is occurring with this particular reagent. We have two steps in this reaction. In the first step, we react with a reagent called BH3. BH3 has this structure. It's actually a dimer with a bridging hydrogen, but we can simplify it by simply writing it as BH3. The hydrogens are actually partially minus in this structure, and the boron is partially plus. So that's the first reagent, and that first step is often run in a solvent like tetrahydrofuran, THF. The second step involves the use of hydrogen peroxide, and as we know, hydrogen peroxide is a powerful oxidizing agent, and it's used in the presence of base. And so it's this reagent that actually introduces the OH portion onto the carbon, leading to the formation of our alcohol. So let's look at the individual steps in the hydroboration reaction. In the very first step, a hydrogen-boron bond adds to the carbon-carbon double bond. And it does so by just simply adding onto the same face of the carbon-carbon double bond. One way to view this is that the hydrogen-boron bond is a quite stubby bond. It's a short bond. And it's not possible for the hydrogen-boron bond to be able to reach around and add the hydrogen to one face of the alkene and the boron to the other face. And as a result, the two groups get added to the same face. So this is a syn addition to what was once our carbon-carbon double bond. Now notice this is not Br2. That is bromine. This is B as in boron, the element just to the left of carbon in the periodic table. It's not okay to use the reagent Br3. That is not a real reagent. We need BH3. It's also not okay to use BrH3. The element is boron. Once we've made this boron-carbon bond in the first step, we can react with hydrogen peroxide and base. And in the process, we oxidize the carbon-boron bond to a carbon-oxygen bond. And this occurs with no change in the stereochemistry. So what was in the first step a syn addition is overall still a syn addition. So let's look a little bit closer here at why, again, it's a syn addition and why we see this non-Markovnikov addition overall in the reaction. So again, here is borane, BH3. And as we mentioned, the boron-hydrogen bond is polarized, so that the hydrogen is somewhat negative and the boron is somewhat positive. So in this particular structure, our hydrogen is actually a nucleophile, and our boron is actually an electrophile. As the BH3 molecule begins to sit down on top of the carbon-carbon double bond, we begin to break the boron-hydrogen bond. We begin to convert the carbon-carbon double bond into a carbon-carbon single bond. We begin to make a carbon-hydrogen bond, and we begin to make a boron-carbon bond. And so this image here is a depiction of what the transition state might look like, with partially broken and partially formed bonds. So it's pretty clear from this that that little tiny boron-hydrogen bond cannot reach to the opposite face of the alkene to put the hydrogen and boron on opposite faces. They must be syn to one another. Now it's a question of why do we see non-Markovnikov addition overall in this reaction? Remember, it's the boron that gets replaced with an OH group. So we have to look in the first step of how does the BH bond add to the alkene. So we said that the hydrogen is actually a nucleophile in borane. We learned in the Markovnikov addition that the nucleophile goes to the more substituted carbon. The electrophile, in this case boron, goes to the less substituted carbon. That's exactly what we see in the addition of HB across the carbon-carbon double bond. The hydrogen goes to the more, and the boron goes to the less. So in the very first step, it in fact is a Markovnikov addition of the hydrogen-boron bond across the alkane. And that's one factor in why this reaction does what it does. The other is that the hydrogen of the BH bond is quite small. The boron end is quite big. And as we add across an alkene, steric effects are also important. The hydrogen, being small, will have less steric strain with the big end of the alkene than will the BH2 group, which is large. So as a result, we match up the small end of the alkene, the CH2 end, the less substituted end, with the bulkier BH2 group. And the smaller atom, hydrogen, gets paired up with the more substituted carbon of our alkene. So this is argued both from the standpoint of Markovnikov's rule for addition of the BH bond and from the standpoint of sterics. So let's apply these reactions to several examples. So our first reaction utilizes the oxymercuration reaction. This reaction simply adds water. It's going to add water in a Markovnikov manner. And so the hydrogen of the water is going to end up on the less substituted carbon, and the OH is going to end up on the more. So let's look at the carbon-carbon double bond here. The right-hand carbon has a pair of hydrogens on it. The left-hand carbon has two carbons on it. And so the left-hand carbon is our more substituted carbon. The right one is our less substituted carbon. And as a result, the hydrogen is going to go to the less, and the OH is going to go to the more. So we'll have our five-membered ring. OH ends up on the carbon of the alkene, which is more substituted, and our hydrogen ends up on our less substituted carbon. Since there already were two hydrogens on that carbon, we'll add one more hydrogen to make that a CH3 group. Now there's no stereochemistry in this problem because we have no chiral center that's formed in the reaction. Now in the second example, we're going to be doing the hydroboration reaction, adding the hydrogen and boron across the carbon-carbon double bond. Overall, water is added non-Markovnikov. That's going to mean that our OH group actually ends up on our less substituted carbon, and our H is going to end up on our more substituted carbon. So we look at the structure and we find out that the bottom carbon is less substituted. The top carbon of the alkene is more substituted. The top carbon will receive the hydrogen. The bottom carbon will receive the OH. And this reaction is a syn addition. And so overall, we're going to have the hydrogen and the OH cis to one another on the ring in the product. So one possible product structure that we could draw is that the hydrogen is added on the top face. The OH group is added on the top face. Or alternatively, the hydrogen is added on the bottom face. OH is added on the bottom face. And these two products are enantiomers. So both of these products can form in the reaction. Let's switch now from alkenes to talking about how water can add to alkynes. In exactly the same way as we can add water to an alkene, and in nearly identical conditions, we can add water to an alkyne. So here we have a carbon-carbon triple bond, and if we react it in one step with a mixture of mercuric sulfate, which is a good source of Hg2+, water, and sulfuric acid, which is a good source of H+, we can actually add water across the carbon-carbon triple bond. Now the product is not what we would expect. The product actually has a carbon-oxygen double bond in the structure, so we need to understand where that carbon-oxygen double bond came from as we start looking at the mechanism of the reaction. That's going to become pretty clear that we do indeed add an H and an OH across the carbon-carbon triple bond, but that an equilibrium happens to give us this product. So this is a Markovnikov addition. If our carbon-carbon triple bond is at the end of a chain, then the hydrogen of the water gets added to the less, the OH of the water gets added to the more. Now let's look at a second set of conditions. We had seen these in the reactions of alkenes. BH3 can add to alkenes, BH3 can add to alkynes. In the addition of BH3 across the carbon-carbon triple bond, just like with alkenes, this is going to proceed by what we call a non-Markovnikov addition. And as a result of that, when the water molecule adds, the OH is going to go to the less substituted carbon, and the H is going to go to the more substituted. So we'll get different products in these reactions. Let's look at the oxymercuration reaction first. So if we start with an alkene and react it in the presence of the mercury 2+, over a series of steps we will add mercury and OH across the carbon-carbon triple bond. And the product that we get then can react with a proton to replace the mercury with a hydrogen. Note that in contrast with the alkenes, we don't have to have a second reagent, the sodium borohydride. The H3O+ will simply do this. The product that we get in this step has an alkene, the source of the ene, directly attached to an alcohol group, which is the ol. And we call these kinds of molecules ene-ol. By simply shifting the red hydrogen here over to the carbon that the OH group is not attached to, we convert an enol over to a ketone. And so this is what's called a keto-enol tautomerization. And it's a mechanism that simply involves acid-base chemistry, pluck off a proton and then put it back on again. But for the purposes of what we're talking about here, let's focus on what happens when we form the enol. Notice that the OH group went to the more substituted end of the triple bond. The H, overall the H of the water, went to the less substituted carbon. And so this was a Markovnikov addition of water. In the case of the hydroboration reaction, in our very first step, we put the smaller H on the bigger end of our triple bond, and our larger boron on the smaller end of our triple bond. And the net effect here then is that the hydrogen and the boron end up syn to one another in our product, with the boron on the less substituted carbon. When we react in the second step with hydrogen peroxide and base now, we replace the boron with an OH group. And now, just like in the previous example, the hydrogen of our enol can move over to the carbon that did not have the OH group on it to give us the carbonyl form of the molecule. In this case, it's an aldehyde. So with the boron reaction, we can get aldehydes and ketones, depending upon our structure. But with the oxymercuration reaction, we will always get ketones. And the reason for that is that if we've got a hydrogen on one end of our alkene, the hydroboration reaction will actually give us an aldehyde because it will deliver the OH group to the carbon that has the hydrogen on it.